Great. So I'll be describing the Extreme Scale Scientific Software Stack project, and it's a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. And we have built a comprehensive, coherent software stack that allows application developers to productively develop parallel applications. And it's a curated software stack based on SPAC package manager. And we have over 100 different HPC packages and also AI/ML packages such as TensorFlow and PyTorch, which are installed with both container-based deployment as well as bare metal deployment. And we support GPU platforms. We also have SPAC build caches, binary build caches, which allows you to install these packages on bare metal systems very quickly. And we support x86-64, IBM Power 9, PPC64, LE, and AR64 ARM platforms with support for GPUs from NVIDIA, AMD, as well as Intel. Of course, on x86, it supports all three of these GPU vendors. On IBM, it supports NVIDIA, and the same for ARM64. And the important thing is these packages are optimized for use of GPUs as well as CPUs. We have container images on Docker Hub and E4S website, and we have a range of different options, including base images as well as full-featured images which support GPUs. And we also have commercial support for E4S from Paratool Sync. And this support helps us for installing E4S on the DOE supercomputers, maintaining an issue tracker for E4S, and also supports AD engagement for ECP. And here are some URLs that you can look at for our latest status. And we also have a AWS image that supports multiple MPI implementations such as these, and a container launch tool that allows you to distribute your applications in a binary form, where we can substitute the MPI in the containerized E4S application with the system MPI. So you could use it on an HPC machine and use, say, the Cray MPitch or the IBM and other variants like Intel MPI. We have quarterly releases. The last release was on August 31st, the E4S 22.08, and we hope to have another release next month. And we also have a virtual box image with support for different container runtimes, such as Docker, Singularity, Shifter, Charlie Cloud. And here is the list of releases starting from October 2018, where we had 24 full products. Now we have 102 full release products in the latest 22.08 release. And it includes packages such as PyTorch, TensorFlow, with support for CUDA, ROCm, GPU runtimes, as well as co-design applications such as Amrex, Kibana, MFEM. You can learn more about E4S from our webpage here. And you can see this, we have a cutoff date for November 4th for submitting new package recipes in SPAC. And here are the containers. You can download a Singularity container with support for CUDA or the PPC64 LE containers and other platforms. We recently added support for ARM64, AR64 with support for NVIDIA GPUs. And this may be of interest as we look at new architectures, including Hopper and Grace Hopper in the future for the Venado system. So how do you use this? If you wanted to just get a Docker image and you wanted to just get it from Docker Hub, you could just say Docker pull with the ECP E4S CUDA, the latest one. And here are the full featured images for AMD, NVIDIA, and Intel GPUs. And we also have the base images for all of these platforms, along with the full featured images. And you can customize the image that you want, starting with the base image. And here are the 102 packages on x86-64 with support for NVHPC 22.7 and CUDA 11.7, which supports both A100 and V100 GPUs with the AI/ML packages as well. And you can see all of these packages such as Butterfly Pack or Feodel, or HDF5. And here is Trilinos and the location where it's installed, and other packages such as PETC and so on, including Tau. And we have support for ROCm 5.2.0. We have Intel One API 22.1.0, as well as all of these runtimes in the container release. This is the same listing for the IBM Power 9 PPC64LE, and you can have a Singularity container that you could deploy on Summit, for instance, with these AIML package versions. And you can see the Trilinos, Tau, and other packages. There are 102 packages here. And this is the listing for ARM64, the AArch64 platform, with support for NVIDIA GPUs with Trilinos here. And if you want to look at how was Trilinos configured, then Trilinos is installed using SPAC, like all these other 100 packages. You can just say SPAC find Trilinos, but show me the version of Trilinos that uses CUDA variant from the SPAC recipe. And in particular, the CUDA architecture of 80, which is for the A100, and it will show you this. You could show the dependency listing in a verbose mode, and then you could see the CUDA arch is 80 and see exactly which packages were configured in, like ePetra, eXT, and so on, and look at how Trilinos was built and what are the dependencies, including this CUDA version over here. And you can, of course, pull directly from the ECP E4S, E4S CUDA to get the container from Docker Hub for all of these different architectures, the 3 different architectures. Here is an example of a SPAC.yaml recipe file, which describes the variants and how Trilinos is built with the CUDA in the SPAC in E4S for the container. And we also have support for a build cache. Now at the University of Oregon, we host a SPAC build cache, which goes way back and includes the latest SPAC 0.18.1 and supports multiple architectures, different operating systems. And you can see that it has now over 92,000 binaries in this build cache. This is the location of the URL. And we also build it on our Frank systems at the University of Oregon. Here's a statistics web page which shows how the SPAC pull requests are being merged, which jobs are being sent to the University of Oregon versus the AWS systems, and the runners and which runners are having failures or what kind of problems there are, and what are the types of jobs that you can see more at stats.e4s.io. We also have the last 4 hours listing and overall. And container images, base container images for different architectures hosted at the Docker Hub with the different GPU runtimes. And our base images also come without GPU support. Here is one which has over 1 million downloads for our SPAC-based image. And also continuous integration images. These are CI runner images that we can easily deploy with GitLab. And these are for all 3 architectures. We also have some custom images, including one for Exawind, where we are using Trilinos. And we have the support for both AMR Wind as well as Nalu Wind packages. And you can see those on Docker Hub. Every night we take the latest version of this application, build it with Trilinos and Cocos, and then post the image on Docker Hub. So you can just go to Docker Hub and see every day's image in this custom image location. We also have GitLab-based nightly testing of Trilinos. Now it's not just enough to create our build cache entries, but we want to actually do a clean checkout of Trilinos every night and look at Trilinos at develop and build it on our systems with support for GPUs and try a test case and make sure that it passes. This is being run on the Frank systems at the University of Oregon, and you can see the URL here to see which which kind of machines we have there. Here is a listing where you can see the different GitLab pipelines, build pipelines. Here, this is past 24 hours ago, 1 day ago, 2 days, 3 days. So every night we are checking out Trilinos, and if there is an error, we notify the developer of this problem. And here is an example of a tpetra run on one of our systems called Saturn, which has a 80 GB A100 GPU. And you can see how we do a SPAC install, and you can see the Trilinos are developed being built with all of these packages with CUDA, and this took, say, 76 minutes to build. And you can see that we are running it on the GPU with CUDA environment variables. And this is the IAllReduce example from the tpetra test cases. And so it runs it on 8 MPI ranks, and you can see the results that they are passed, and then it logs all of this info in GitLab. And anybody can access the GitLab GitLab information from gitlab.e4s.io/uo public location. We also have a validation test suite where we can run this example, and in this case we have a clean.sh, compile, run, and setup.sh. And we also do this testing on Perlmutter at NERSC to make sure that we allocate 2 nodes, and then we are able to compile and run it using their internal GitLab system. And we also have an AWS image. As you can see over here, we have a view of Trilinos output from the Nalu wind test case. And we use Tau to look at the performance of this. We look at ParaView to see the performance of this application run. And this is with the E4S 22.08 image. Tau performance system supports the Cocos profiling interface. And you can see all the details of the execution of the kernels with no change to the binary. So you can see the detailed performance data and where the time is being spent in the various kernels, and right down to the Cocos parallel for level, and zoom into the source code, and you can see the different options that are there. So we have a remote desktop running on AWS. This can be very useful in giving tutorials. So if you would like to use this, please get in touch with me. I can launch the AWS image and have a remote desktop running for every one of your, say, 100 tutorial participants for that duration of time. And they can log in, they can try running the applications. We also have a local build cache in this. We also have full-featured Singularity containers of E4S. And you can see a list of all of these different options. This is based on AWS's DCV remote desktop software. And we have a tool called E4S Container Launch, or E4S CL, which helps simplify the launch of MPI jobs which use the E4S containers. And we use this tool to replace the MPI libraries so that you could have an MPitch-based application which uses the Trilinos in the container, and then we substitute this MPI with the system MPI using the MPitch ABI as well as Y4MPI if you're using OpenMPI. So both MPitch and OpenMPI cases are supported. We can just need to specify 3 different things when we launch the E4S CL tool. We need to initialize it and tell it what kind of container runtime it should use, whether it's Docker, Singularity, Shifter, where is the image located, and what it should launch as startup commands when the container is initialized. And once you do this, it figures out which libraries need to be substituted and mounts them from the host system in the container image, so that when you say E4SCL MPI run command, it will know which libraries to take care of and puts them there in the right place. You can specify a startup script like this, and you can put that in that script. You could say, bootstrap the SPAC and then load the Trilinos version with CUDA with support for A100 GPUs in this startup script. And then when you run the npi run command, it will then do these commands and start up the application and run it. So in summary, what is E4S? E4S is an extensible open architecture software ecosystem that accepts contributions from US and international teams. It's a framework for collaborative open source product integration. It's not a closed system that only takes contributions from DOE teams. And it's not a monolithic take it or leave it software behemoth, but a full collection of compatible software capabilities and a manifest of a la carte selectable software capabilities where you can start with a base image and then you can construct your own custom images using E4S. You can use it for installation on HPC systems with bare metal installations. It's a vehicle for delivering high quality reusable software products. And I think of it as a conduit for future leading edge HPC software targeting the scalable next generation computing platforms. And it's a hierarchical software framework to enhance via SDKs the software interoperability and quality expectations. It has also emerged as a top level component in the DOE HPC community, which enables new relationships, including with other agencies, industry partners, and international collaborators. And we are expanding this portfolio to include new domains like ML, AI, and operating system lower level components. And the goal is to provide better, faster, and cheaper capabilities. Much of this work on E4S goes on at the Performance Research Laboratory at the University of Oregon. We have a very active visitor program. Please consider coming to Eugene and spending a couple of days with us and working through some of the issues that you may face. And I would like to thank the Exascale Computing Project for their support of E4S. And with that, I would like to take any questions.
Thank you, Samir. Have questions?
So are the simulation tools, are they available via Docker or, virtual machine images?
Would you please repeat that question? Are the simulation tools available through Docker?
Yes.
Yeah. So all of these are available through Docker as well as Singularity. And they are available on the web page. You can just directly go to the Docker images, or you can do a Docker pull on your own system, and you can get access to the full featured images as well as base images like these. Does that answer your question?
Yes.
Any other questions?